Lecture we have discussed about the half wave rectifier and calculation of its efficiency. Now we are going to discuss about the full wave rectifier. One of the main disadvantage of the half wave rectifier is that we will get output only during the positive half cycle and the negative half cycle is completely cut off. Here the current flows through the through the load resistance in the same direction for both half cycles of the input AC voltage. So that is the main advantage of a full wave rectifier. Usually the full wave rectifier can be constructed in two ways. One is called a center tapped full wave rectifier and the other one is full wave bridge rectifier. The case of first of all we will discuss about the center tap full wave rectifier. The center tap full wave rectifier is given by this. This is the schematic or the circuit diagram of a full wave center tap to full wave rectifier. Here the AC supply is again applied to a step down transformer, and the transformer here the condition is that the step down transformer should be having a secondary. We should be having a center tap to one. That means the A is one end and B is another end, and this O is the center tap of the secondary of the transformer which is used to step down the input AC voltage. Now the end A is connected to the diode D1 and end B of the secondary winding of the transformer is connected to the D2, and they are joined together and is connected in series to a load resistance RL, and the RL is connected to the center tap of the secondary winding. Now this forms the circuit of a full wave center tapped rectifier. Now let's see the operation of this diode, this rectifier. During the positive half cycle, say at the end A is positive and end B is negative. That is, if we consider this end to be positive and this end to be negative, then this D1 is forward biased and this diode D1 is forward biased and D2 is reverse biased. So D1 conducts and D2 does not conduct. So during the positive half cycle D1 conducts and the current will flow in this direction through the load resistance RL. Now during the negative half cycle, that means the this end become positive and this end become negative, that is end B is positive and end A is negative, then the diode D1 is reverse biased and the diode D2 is forward biased. So D2 conducts and D1 does not conduct. So this D2 conducts means that the current flows through this circuit in this direction, and the current in the load resistance is again from this end to this end during the negative half cycle also. So we will get an output voltage like this. During the positive half cycle D1 conducts and the current through the load resistance is in this direction, and during the negative half cycle current in the load resistance is same and is in the same direction as that of the previous case. So D2, when D2 conducts, the current through the load resistance is again in this direction, and this cycle is repeated again and again. So we will have a pulsating DC like this. And here one of the important thing we have to note down is that if Vm is the voltage across this AO, and the voltage across OB is again Vm, let it be. Then the peak inverse voltage will be 2 Vm. So that is very important thing in the case of a full wave center tap rectifier. That is peak inverse voltage is twice the voltage of this output of the maximum output of the center tap rectifier, center tap transformer output. And the disadvantage of this center tap full wave rectifier are it is difficult to locate the center tap on a secondary winding. It is the general difficulty. Once we are getting a center tap rectifier, it is okay. But usually it is very difficult to locate a center tap. And another one is DC output is small as each diode utilizes only one half of the transformer secondary voltage. That is A to B is the total secondary voltage. So if you consider this is Vm and this is Vm, so total of actually we are having 2 Vm as the secondary output voltage, but we are getting only Vm as the output voltage across the load. So we are getting only one half of the transformer secondary voltage across the load resistance. So it is a very a big disadvantage of this center tap full wave rectifier. And I told you the peak inverse voltage is twice the voltage of this one. That is whatever the voltage appears across the secondary of the transformer will be appeared as the peak inverse voltage of the voltage across the diodes. So the diodes used must have high peak inverse voltage compared to the other rectifier, that is full wave bridge rectifier, which we are going to discuss. Now let's see the full wave bridge rectifier. From here onwards your curriculum actually starts. That means your Calcutta University syllabus prescribes these portions from this onwards, the full wave bridge rectifier onwards. But to understand this action and working of a full wave rectifier, bridge rectifier, we should know the action of a crystal semiconductor diode or crystal diode, how a half wave rectifier works, how a center tap bridge rectifier works. Now let's see the full wave bridge rectifier. Now this is the circuit diagram of a full wave bridge rectifier. The name, as the name implies, there is a bridge in this circuit. You may be heard about different types of bridges. Here we are having a bridge which is formed by four diodes D1, D2, D3 and D4 connected in this manner. In between these two junction, two nodes or two junctions of opposite junctions of the bridge, a secondary of the transformer is connected, and the other two opposite or diagonal corners of the bridge we are connecting the load resistance. From there we are getting the output voltage. Now let's see the action or the working of this diode. Suppose during the positive half cycle this P is positive and Q is negative, let's say. Then this current starts to flow in this direction. When it reaches at this point, this diode D4 is reverse biased and it does not conduct at all. But this D1 is forward biased, so it starts to conduct, and the current flows from A to B through the load resistance, and at B this current flows through this D3 and it is forward biased, so it flows in this direction. Since when it flows from at reaches and A, this diode D2 is reverse biased, So during the positive half cycle, diode D1 and diode D3 are forward biased and diode D4 and D2 are reverse biased. So D1 conducts and D3 are conducts during the positive half cycle. That means current from uh, through the load from A to B, there is a current flow. So this diagram will show you exactly what happens during the positive half cycle. From P starts to flow in this way from A, then to through the resistance it starts to reaches the point B, and then D3, and it completes the cycle during the positive half cycle. Now consider the negative half cycle. During the negative half cycle, that means let's say the end P is negative and Q is positive, then current reaches at this point. This diode D2 become forward bias, then D3 become reverse bias. Similarly, here it is negative, so diode D1 become reverse bias, then D4 become forward bias. So D2 and D4 become forward bias, then D1 and D3 become reverse bias. That means D2 and D4 conducts during the negative half cycle. So that the current will again, here it is positive, so current will flow in this direction, and it is flowing through D2 since it is forward biased. After reaching the point, it actually comes to flows through the load resistance again and reaches the point B, and then it is goes to flows through D4 and reaches the point B, and so that it completes. So during the positive half cycle, if you this is the output waveform of a full wave bridge rectifier, and during the positive half cycle D1 and D3 conducts, we will get an output like this. And during the negative half cycle or the other half cycle, D2 and D4 conducts, and we will get another cycle like this. So we are having a full wave rectified output. Again, it is a pulsating DC, and it is similar to the output is similar to the output of a center tapped rectifier. But remember that the peak voltage, whatever the voltage appears across the secondary, that is PQ, will appear across the load resistance RL. In the previous case, in the center tapped one, whatever voltage appears across AB will not appear across RL, but only the half of AB, that is the voltage across AO, will appear across RL. So we will get two times the output voltage than that of the center tap rectifier. So let's see the advantages and disadvantages of the full wave rectifier. Here the advantages are the need for a center tapped transformer is eliminated because there is no need to have a center tapped uh, here. And I told you the output voltage is twice that of the center tap transformer for the same secondary voltages, and the peak inverse voltage is one half of the center tap circuit for the same DC output. Since because whatever voltage is appears across the center tap will appear across the diode, so peak inverse voltage will be half for the same DC output. Now the disadvantages are it requires four diodes. So four diodes means it become little bit bulky and expensive. Not that much expensive, but when compared to center tap, it is requires four diodes. The another one is that during each half cycle of AC input signal, the diode that conducts are in series. Therefore, the voltage drop in rectifier unit will be twice as great in center tap circuit. This is subjectable when the input voltage and output voltages are very low. If the input voltage and output voltage is very high, then it is not doesn't matter. But if you consider this one, if you, during the positive cycle this D1, then the resistance RL, then D3. So D1 and D3 are in series, so there is a RF for D1 and there is a RF for D3. So two RF, we have to add, the total voltage drop will be 2 RF, that is I into 2 RF will be dropped across D1 and D2 there, since they are in series. So there is a little loss in this full wave bridge rectifier. And another important advantage is that the output frequency. And as you know, from this diagram you can see that this is the input signal 0 to 360 degree, but here at every 0 to 180 degree it is the advantage of a full wave rectifier. Actually, for center tap also we will have this value, that is output frequency will be, so this is the period 180 degree, here it is period is 360 degree, so period is twice here, so frequency will be half here, so output frequency will be twice the input frequency.